We have learned how ideal gases behave through a series of laws, and we also have had an explanation for why ideal gases behave that way through the kinetic molecular theory of matter. Today we're going to look at exceptions to this. Gases, in fact, over a wide range of ordinary pressures and volumes, are going to follow the ideal gas law fairly well. But there are some times when that will not be the case for real gases. They don't always fit the ideal model. So we're going to look at when and kind of a why and what to do about it in this video. So let's compare real versus ideal gas behavior. If we take the ratio PV over RT, that's the number of moles, and as long as you have an unchanging number of moles, that's going to be a constant number for an ideal gas over all pressures. But for real gases, there is some deviation, and here we see 4 real gases plotted out. Their actual ratio of P to V over R to T over a number of different pressures. We can see that they deviate pretty significantly from what would be expected from ideal gas behavior. Now, this is mostly only an issue when the pressures are quite high. If you look at the scale here on the horizontal axis, this first tick mark is 200 atmospheres, 200 times normal atmospheric pressure. If we're talking about 1 or 2 atmospheres where we normally live in regular times, we're talking about a deviation that's pretty small. And so therefore the ideal gas behavior for most ordinary circumstances is a pretty good approximation for how gases are going to behave. Why does this deviation occur? Well, for one thing, the kinetic molecular theory that ideal gas law is based on assumes that particles don't have any volume, that they're point masses and they don't actually take up any space. And that's not true. Particles actually do have volume, and when the actual volume of the gas gets compressed down to a small enough space, you can no longer ignore the fact that these particles themselves actually have some volume. And the other assumption that KMT makes is that the particles don't interact with each other, that the collisions are perfectly elastic and that the particles always move in a straight line. And in fact, we know that particles do actually have attractions for each other through intermolecular forces. These deviations are most noticeable under 3 conditions. One, when the pressures are high. The reason for this is because that means the extra space is going to be small between the particles. If the pressures are high, that means there's going to be a lot of collisions, and that probably means that you have compressed your volume down to a small volume, or there's a lot of particles in the volume that you do have. And so that means a few things. One of them is that the ideal gas space, the supposedly empty space, well, that becomes less and less of a usable presupposition. Another one is when the intermolecular forces are high, and that's because the particle interactions are less ignorable when you have particles that are more highly attractive to each other. And then the third thing is when temperature is low. And the reason for that is because we're making the assumption that particles never lose any energy when they undergo collisions, and that's not true. The reason that it works as an assumption is because there's always extra ambient energy that can make up for the tiny losses that we experience during those collisions. But when the temperature gets lower and lower, we see that there's less extra energy to make up for those losses that occur during collisions, and so we get deviations from ideal gas behavior. So let's build a more precise model that can compensate for that. Here's a thought experiment. Imagine that this is the actual volume of a container that contains a gas. Let's split it into 2 spaces. One space will be the volume of the actual particles. So imagine that you take all the particles and squish them down so that basically they're a liquid. You push all those particles into the smallest space they can occupy. That's the volume of the particles. And the rest of it is empty space. That's the ideal gas volume. That's the volume that you're assuming that you have under the ideal gas law. So the total volume, the actual measurable volume, is the ideal gas volume plus the volume of the particles. And because the ideal gas law is built on this ideal volume, we could say P times V ideal equals nRT. So V ideal is the total volume minus the volume of the particles. So we could rearrange the ideal gas law in this way. We could say that the pressure times the actual measurable volume minus the volume of the particles is equal to N times R times T. But the volume of the particles is going to be proportional to the number of particles. So if we introduce a constant of proportionality, we're going to call B here, then pressure times the actual volume minus the number of particles times some constant number b is equal to n times r times t. And that constant number b, that's related to a particular gas. And of course, this is going to be a bigger deviation if those particles are larger. So bigger particles are going to have bigger b values. So the bottom line is, bigger particles are going to result in a higher value of b, which means a bigger deviation from ideal gas behavior. The other thing that we have to compensate for is particle interactions. And here's how we're going to do it. Particles that are near the wall experience a net pull away from the wall. So imagine this particle is going to collide with the wall, and that collision is what makes pressure. It's all those collisions with the wall. That particle that's near the wall, there are more attractive particles on the inside than there are on the outside because it's not attracted to the wall like it is to the other particles of its own kind through IMFs. So because of that, the collision force that that particle is going to put on the wall is less than it would be if it really was not attracted to the other particles, which is the ideal gas assumption. So that means the pressure that you would actually measure by particles hitting the walls of this container is less than what you would expect from the ideal gas assumption. Now, the number of particles to interact increases with the density of particles. And the density of particles, we can think about that as the number of particles divided by the volume. But the number of particles that those particles have to interact with also increases with the density of particles. So this factor should be accounted for twice. So therefore, the reduction in pressure is going to be proportional not to the density of the particles, but to the square of the density of particles. So taking that into account, we can modify the ideal gas pressure by adding to the measured pressure this factor for the missing pressure because of intermolecular forces. So because that's proportional to the square of the particle density, we can multiply that by a constant of proportionality, and this one we're calling A, and that makes a modification for pressure in the ideal gas equation. So bottom line, stronger IMFs are going to mean a larger value of A, and that's going to mean a bigger deviation in pressure. So the pressure that you would actually measure is going to be less than the ideal gas pressure by a bigger quantity when the IMFs are stronger. And higher particle density is going to also result in a bigger deviation in pressure because the number of particles packed into that volume is larger, and then the square of that quantity also makes a difference in how much pressure deviates from ideal gas pressure. Now, if we put both of these factors together, we can take PV equals nRT and modify it by compensating for pressure by using this factor. Pressure is actual pressure plus A times the particle density squared. So that's the P. And then remember, we compensated for deviations from ideal gas volume by taking V minus the number of particles times that constant of proportionality B. So there's a B and an A for every real gas that we can plug into this equation, and that will calculate the nRT. So this is a compensation that makes a better model, at least a model that's usable over a wider range of pressures and temperatures, by modifying the ideal gas law in this way. This is called the van der Waals equation. There are other equations that use a slightly different approach. They also basically do the same thing to modify the ideal gas law. Van der Waals equation is one of the more common ones, though.